All right, last class we left off talking about separating mixtures. We also talked about states of matter. We talked about our solids, our liquids, our gases, and the ways that they're different. Our solids and our liquids, our molecules, our atoms, our small little pieces are all touchingly close. They're interacting with their neighbors. Our gases are separated, there's space in between them. Our liquids can also move freely around each other. That's why liquids will flow. Solids can't move past each other. That's why they stay put. There's also changes. There's two types of changes. One of them is physical changes. A physical change alters the state. The three that we were talking about: solid, liquid, gas. Or appearance, but not the composition. So if you were to zoom in to the molecular or atomic level, you would see that all the building block pieces are exactly the same as before you made it go through this change. So the atoms or molecules in the substance do not change their identities during a physical change. For example, when water boils, it's changing from a liquid state to a gas state. In the gas state, it's still water molecules. They're just separated in space. So that would be a physical change. All state changes, solid, liquid, gas, all of those state changes are going to be physical changes. Chemical changes, on the other hand, alter the composition of the matter. So if you were to zoom in to the atomic, the molecular level, the chemicals change. So we've got different chemicals before/after, or before and after, rather. So our atoms rearrange themselves in some way, and we've got something different than when we started. So one example of that might be iron. If you take an iron nail and you leave it out with some water or some acid, and it stays wet and it's got time to react, it might turn into iron oxide or rust. So it went from being just iron atoms, and now it's got iron and oxygen atoms incorporated in there. So it is fundamentally a different chemical. So that would be a chemical change. Another example of a physical change would be dry ice subliming. Subliming is when you turn from a solid to a gas. You just straight up skip the liquid phase. So dry ice is carbon dioxide, and it will sublime. So at normal atmospheric pressure, you won't be able to observe liquid CO2. It doesn't exist. That would also be a physical change. Sugar, if you dissolve it in water, when you dissolve something in water, the particles get pulled apart. In the case of something like sugar, sugar is a molecule, and so when it dissolves, the sugar molecules get pulled apart from each other, but in the solution they're still sugar molecules. They've just been separated from each other. It's not exactly the same as turning into a gas, but it's similar. So for things that are molecules, dissolving is also a physical change, because before and after, it's still sugar. It hasn't changed into anything else. One odd exception, or one class of odd exceptions for dissolving. So molecules, which we'll learn our definition for molecules later. Molecules, things like sugar, when they dissolve, it's a physical change. Something like salt, when it dissolves, you're actually breaking apart the sodium and the chloride. In the case of table salt, you're breaking those apart into separate ions, and so in solution, it's actually different than what you had as a solid, and so that would be a chemical change. So for salts/ionic compounds, this would be a chemical change because the ions are separating from each other. Another example of a chemical change is propane gas burning. So propane is commonly used for barbecuing. Most outdoor grills run on propane. And when propane gas combines with oxygen and a little bit of heat, it burns, and so it turns into CO2 and H2O. What you had before is different than what you had after. And so that makes it a chemical change. It's undergone a chemical reaction. There's also, beyond just changes, there's also properties. So physical properties are displayed without changing composition. So for example, smelling gasoline. It's a good thing that this one is a physical property, because otherwise you go to the gas station, you accidentally smell your gas. Oops, all my gas is gone, it's something else. That would be a big bummer. So smelling gasoline, before you smelled it, it was gasoline. After you smelled it, still gasoline. So odor or smell, taste, often, color, appearance, melting point, boiling point, density, these are all physical properties. Melting point and boiling point, these are related to physical changes. So they're physical properties. For color, that one's easy to tell, right? What color is my shirt? Green, maybe a mint green. Is it still mint green after we've observed the color? Sure is, right? Nothing's changed. So those would be examples of physical properties. There's also chemical properties that are displayed through a chemical change or a chemical reaction. So for example, the flammability of gasoline, you can't show somebody that gas is flammable without burning it and turning it into something else. Like we saw in the previous slide with propane. You can't burn propane to show somebody that it's flammable. It produces a flame without turning that propane into something else. So that would be a chemical change. Corrosiveness and acidity and toxicity, those also typically involve the chemical that's causing the corrosiveness, that's causing the acidity, that's causing the toxicity. Usually involves those turning into something else, usually. And so all of those things, corrosiveness, acidity, toxicity, would be examples of chemical properties. They have to be displayed by a chemical change. All right, for each of these, let's think about, are these changes physical or chemical? What kind of property is demonstrated in each case, physical or chemical? So a copper wire is hammered flat. Is that a physical or chemical change? Physical. It's a physical change. Before we hammered it flat, it was copper. After we hammered it flat, still copper. What kind of property did it display? Did it display a physical or chemical property? Also physical. Physical property, we're looking at the malleability of copper. It can be hammered flat through a physical change. A nickel dissolves in acid to form a blue-green solution. Is that a physical or a chemical change? This one would be a chemical change. What kind of property has been demonstrated? This one's chemical. Chemical changes and chemical properties go together. The property would maybe be the ability of the acid to dissolve nickel. The reason that it changed color, nickel is kind of like a whitish metal, silvery metal. When it dissolves into the acid and forms that blue-green solution, the color change is one way that, one thing that might indicate to us that it's a chemical change. Color changes are often, always, chemical changes. Dry ice sublimes without melting. This one's physical. Why is it physical? It's the same before and after. All that it did was it changed from a solid to a gas. Phase changes or state changes are always physical changes. And it would also be a physical property. Weird how they keep going together like that. A match ignites when struck on a flint. before and after striking the match, are they the same or are they different? Different, right? So it's chemical. You can't unignite it and then reignite it. And this would also have a chemical property, the flammability maybe of the phosphorus I think they use in match tips for the strike anywhere matches. Questions about any of those? Great, we're cruising. The diagram on the left represents liquid water molecules in a pan. Which of the three diagrams, A, B, or C, best represents the water molecules after they have been vaporized by boiling? We've got guesses for A. Any other guesses? Cool, A is the correct answer. A is correct. Before we have water molecules, it's the two white dots on a red dot. In A, we've got two white dots on a red dot. They're separated by some space. In B and C, we've got oxygen molecules and hydrogen molecules. Those are different than water molecules. And in C, we've got monoatomic oxygen and hydrogen, which is also different than water. So going from our reference state on the far left to A, we have the same chemical before and after, the same shape piece before and after, whereas B and C are different, and so those would be chemical changes. All right, scientific measurements. Hopefully you're all somewhat familiar with a lot of this stuff that we're talking about. Chem 1 is a lot of review from Chem 20. So I tend to try to go a little bit faster. We'll see if I can avoid getting sidetracked. So scientific measurements are reported so that every digit is certain except the last one, which is estimated. And oftentimes what we mean by estimated is just it could be a little bit higher or a little bit lower. So I'm going to write that as a little bit plus slash minus. So it could be slightly higher, could be slightly lower, but the other digits, the ones that are in front of that last digit, we're certain about all those. We're 100% sure about all those numbers. So for example, for the carbon monoxide concentrations in LA County for the years over here, carbon monoxide concentration in 1990, 9.9 parts per million. That means we're 100% sure about that first 9. It's definitely 9 parts per million, which is a measure of concentration. The 0.9 could be maybe 0.89 in reality, could be 0.91, could be a little bit higher or lower, but it's definitely not 10, it's definitely not 8. Right? It's definitely the 9 here for the first place. The second one could actually be a little bit higher or lower. There's a little bit of estimation in there. So representing it this way, we've got one certain digit, one certain decimal, and one uncertain. When we represent it in these other numbers, this 9, for example, could be 9.4-ish in reality, could be, I don't know why I drew my 8 like that, could be as low as 8.6. There's a lot more plus or minus because we don't have the same level of number of digits. Are we saying that? Hopefully. When we do measurements, the number of digits recorded depends on the measuring device. We are always going to, quote unquote, read between the lines. What this means is that we estimate one decimal place past the smallest division. This only applies for analog measurements. Who knows what the opposite or the counterpart of analog is? Huh?
Dialogue?
Not dialogue. Think about clocks. Digital. So an analog clock has the hands and you have to read the time, right? Digital clock just tells you what the time is. It's the same for analog measurements and digital measurements. For analog measurements, you have to look at the instrument, you have to look at the device and come up with the numbers yourself. In a digital measurement, you are just given the numbers. So most of what we're going to talk about is for analog measurements, because that's kind of the tricky ones. For digital measurements, you just write what you're given. That's why we don't talk about that much. Literally whatever you're given from the scale, the balance, whatever it is, you just write those numbers down. For analog, we can estimate a decimal place past the smallest division. So for example, on this scale where we've got pistachio, right? My brain is fried today. A pistachio, we've got a scale that's in grams. We're going to read the gram side because reading grams is nicer than ounces. And our markings, we've got our 0, computer, enhance. We've got our 0 up here, our 10 down here. These individual markings are going to be 1. So we've got our smallest measurement, our smallest increment as 1 gram. We are past the 1 gram. We're not quite to the 2 grams. So we're for sure certain. We would all agree, hopefully, we're past 1 gram. Lock in 1 gram. How far from 1 gram to 2 grams are we on a scale of 1 to 10? We're a little bit past from 1 to 2, so we might be 1.2. That's why 1.2 is the estimate here. You might see it as 1.3 or 1.4. That's okay. There's usually, with analog measurements, we could get 2 or 3 different readings, just kind of depending on who's reading it. So the 1 here is certain. The 0.2, that's our estimate. It looks to us like it's 2 out of 10 on the way to 2 grams. It's not absolutely critically important that you get the exact right estimate. What's important is that you do the estimate. That's arguably the most important thing. Obviously, we want to be close. We want to be doing it correctly, but it's more important that you do the estimate than that you're absolutely perfectly right on. Again, it is an estimate. All right, so let's report the correct number of digits for these measurements. On the left, we've got a thermometer. On the right, we've got probably a 10 mil graduated cylinder, and we're trying to read the volume. Let's start with the thermometer. So let's get a grasp of our bearings. Right, we've got our 100 degrees. Let's assume it's Celsius because this is a chemistry class and we're probably using SI units. So 100 degrees Celsius or metric units. And this 10 to the right would then be 110. 110 degrees Celsius. We've got a big tick mark in the middle. That would be our halfway point, and then small tick marks between our halfway and our big marks. So these individual markings would each be 1 degree Celsius. And if we look at where our red line is, it looks to me like we are definitely past the 1, the 2, probably also past the 3. How do we feel about that? So we can lock in 103 degrees Celsius, and then how far past the 3 to the 4 are we? Some of you might say, looks like we're right on it. I think that would be fair. If we're right on it, what would we record for our estimate? 0.0. So you might see it is right on the number, so we'd add a 0.0. You still have to add a number even if your estimate is that it's right on the mark. Your right on the mark number would just be a 0 for the next decimal place. You might also read it as a 1 or a 2, or possibly even a 3. It's definitely not a 5 or higher. Questions about doing that measurement? Cool. For our volume of presumably water that we've got here on the right, this is in a graduated cylinder, tall, skinny cylinder with a usually hexagonal base. and we've got water in there. And the way water interacts with glass, which our graduated cylinders are made of, it likes glass. And so it will crawl up the walls of the glass a little bit. And that's why we get this curved shape here. So all the way around the graduated cylinder, the water is climbing up the walls just a little bit. But for the most part, this middle part is empty space. And so we want to read from the bottom of the curved shape, the bottom of the meniscus. That will give us the best reading. So we would get down to eye level with the bottom of the meniscus and then estimate where we are. So let's get a bearing on our numbers. We've got 4 here and 5 here. So we're definitely between 4 and 5, but we have smaller markings. Those smaller markings would be what? What would one of those jumps between small markings be? 0.1. So we've got 4.1, 0.2, 0.3, 0.4, 0.5. Looks to me like we're above the 4.5. We're not quite to the 4.6. So we would lock in 4.5. And then how far above the 5 on our way to the 6 are we? We're maybe halfway, we're maybe a little bit past. So what would we write down for our estimate part? We've got 4.55, maybe 4.56. So the 4.5, this is certain. All of us can agree on that. And then the part here in red, this would be our estimate in units of probably milliliters. Questions about measurements? We have a whole lab that we're going to do that's all measurements next week. So we'll get to have lots of fun making analog measurements and some digital measurements, I think, too. When we are taking measurements or when we're provided numbers, we have to consider significant figures or sig figs, or significant digits, some people call it. So the precision of our measurement, how finely we can measure, like what's our smallest marking, the precision depends on the instrument that we use to make the measurement. If I was measuring how tall people are in the class and I just have a yardstick, it doesn't have any markings on it, it's just 3 feet long, I wouldn't be able to get very good measurements. I would be able to say, yes, you're above 3 feet tall, but you're not quite 6 feet tall, or yes, you're a little bit above 6 feet tall, but I wouldn't be able to provide much more information beyond that. Our estimate would be pretty wishy-washy. Versus if we use a tape measure, then we can get down to the inches and maybe even estimate between inches depending on how precise we want to be. So that's what we're talking about here with precision of the measurement. We want to make sure that when we are doing calculations that we are accurately portraying how precise we were with our measurements. If I'm measuring people with yardsticks and I'm reporting your height in feet, we wouldn't expect me to say you are 5.55687 feet tall, because that's way too precise. And we also wouldn't want to carry that through if we had to do calculations, like if we were converting it to meters or something. So significant figures and our rules for managing significant figures is our way of keeping track of our uncertainty, keeping track of how precise our measurements were, through to our final reported calculations that will go in our tables in our labs that we submit. So our significant figures or significant digits, we've got rules. Here's the rules. At the end of this course, I expect you to know the rules. And so do I. So please learn them. The sooner that you learn them, the less painful labs will be, because I will mark for significant figures for at least most of the labs, unless I just get sick and tired of it, and then I might stop considering them later in the course. Don't count on it, though. So for significant figures, all non-zero digits are significant. Anything that's not a zero, so things that are 1, 2, 3, 4, 5, 6, 7, 8, and 9, all non-zero, those are always significant. Easy. Interior zeros, zeros that are between our non-zero numbers, are also significant. So those are bolded in these two examples. Our leading zeros, zeros that are out in front of our first non-zero number, are not significant. Trailing zeros are a bit of a mixed bag. We've got instances where trailing zeros are significant, and that's if we have a written decimal point. So if there's a decimal point, then all of our trailing zeros are significant. If we don't have a written decimal point, then those trailing zeros are ambiguous. They might be significant, they might not be significant. So in the case of 100,000, we definitely have one significant figure because the 1 is a non-zero number. Any number of those zeros after it, any number of these could be significant. It could be that 2 of them are significant, but we can't tell that based on the way that it's written. It could be that all of them are significant, but we can't tell that based on the way that it's written. So we would want to put these in scientific notation. For example, if the 100,000 has 2 of those zeros being significant, 1.00 times 10 to the 5, whatever the units are. So now we've got a written decimal place, so our trailing zeros, the 2 that I put behind the decimal, those are both significant, and we can see that. Questions about significant figures? Office hours would be a great place to come if you've got questions about significant figures. Office hours start next week, 8:45 to 10 a.m., either in my office or in the STEAM room, as they're calling it, in the library. There's also exact numbers. Exact numbers have no uncertainty. These are typically things that are countable in whole numbers, would be one way of putting it. I think that's a little bit nicer than exact counting of discrete objects, although that is a very good description. Countable in whole numbers, I think, captures a little better. So for example, if we were to count up the number of people, the number of bodies in the room, let's say that there's 29 bodies, which is not true, 27 bodies in the room. Would anyone dispute, assuming that 27 is the correct number, would anyone dispute that there's 27 bodies in the room? What about 27.1 bodies? Would that be accurate? No. What about 26.5 bodies in the room? No, because one of us would be going to jail if there were 26.5 bodies in the room, right? Well, maybe not one of us, but somebody would be going to jail, hopefully, right? We know that each individual person, each individual body, despite differences in size, one body per thing, right? We understand that. So it would be an example of exact counting of discrete objects. There's also integral numbers that are part of an equation. It's like if you're calculating diameter, it's 2 times the radius. The 2 there is an integral number that's part of an equation. There are also some defined quantities. Some of our conversion factors, like 1 gallon is defined as 4 quarts. A mile is defined as 5,280 feet. Not all of our conversion factors are going to be defined quantities. Usually, if a number has, like in an equation or in a conversion, if it has decimal places, it's not exact. This isn't always true, but usually, if there's decimal places, it isn't exact. That's my like general rule of thumb. A lot of constants aren't exact. We haven't gotten to any constants yet in the class, so I can't give you an example. Questions about exact numbers or significant figures? Yes?
When would it be exact?
If it's just like the 1 gallon equals 4 quarts, like 4 and 1 are both whole numbers. So if we had to guess, yeah, it's probably exact. For a lot of our other conversions, especially between metric and English, the ones that we're used to, like if you were converting from gallons to liters, 1 gallon is like 3.785 liters. It's got decimal parts on it, so it's probably not exact. There's one notable exception that I'll point out here. 1 inch equals 2.54 centimeters. This one is exact. The story that I found about this was that they were really, really close. So it was like 2.54 and then like 3 zeros after that. It was like super, super close. And so scientists were like, hey, that's super close to being like exactly 2.54. Can we all just agree to call it 2.54 centimeters and 1 inch? And so we changed the inch, I think, so that works out to be exact. So that's kind of nice. That's one of my favorite conversion factors. All right, these numbers, let's determine the number of significant figures. For A, we've got 554 kilometers. We've got 3 significant figures. We've got 3 non-zero numbers, they're all significant. How about B, 7 pennies? It's not 1. It's not 2. It's not 3. If you counted out 7 pennies and gave them, you were buying something that cost 7 pennies at the grocery store, and you handed them to the cashier and they said, ooh, you provided me 6.9 pennies. Excuse me? What do you mean I provided you 6.9 pennies? Right? You gave them exactly 7 pennies. That's 7 cents. Unlimited. This is an exact number. So anything this falls under this exact counting of discrete objects or countable in whole numbers. It falls under that category. It's an exact count. There's no uncertainty about it being 7. It's exactly 7. We could add as many zeros as we wanted to. So that would be infinite sig figs. What about 1.01 times 10 to the 5 meters? 3. We've got our non-zero ones, and we've got an interior 0. What about D? This one is 2 significant figures. The reason that the zeros in front don't count is because they're leading zeros. So those don't count. Did we learn how to do scientific notation in this class? I'm already taking crazy pills. It's day 2. All right, I'm just going to assume that we know how to do scientific notation. If we were to turn this into scientific notation, what would we write for the decimal part, the part that goes in front? We would write 9.9 for the front part, right? We wouldn't write 0.0009.9 because that looks crazy. The leading zeros are not important. All right, 1.4500 kilometers. How many? 5. We've got 5 significant figures. We, of course, have our non-zero numbers. We've also got two trailing zeros. With a written decimal point. And then for F, 21,000 meters. 2, 5. It's not infinite. It's ambiguous. So this one's at least 2. Possibly as much as 5. We would want to write it in scientific notation to properly reflect the number of significant figures that it should have. So we don't know because we didn't take the measurement, we didn't do the calculation to get that number. So we would just say, I don't know, it's at least 2. Question? On the exams, for the most part, it's going to be true, false, multiple choice. Most of it. And so you would just pick one. It might be in scientific notation, depending on whether significant figures are considered. On free response questions, it would be correct in scientific notation or in standard notation. If it's an ambiguous case like this, then I would want to see it in scientific notation so that you've got the correct sig figs shown. One little hack that you can do if this 21,000 was 5 significant figures, and you don't want to write it in scientific notation for some reason, 21,000 dot. Now we've got a written decimal place, so I would consider those zeros significant. So if all the zeros are significant, you can just add a dot. You don't add a 0 at the end, just add the dot, and that's good enough for me. Any questions about any of these? Great. We will also use significant figures in calculations. So the results of the calculation must reflect the precision of the measured quantities, the significant figures of the measured quantities. We don't want to gain extra decimal places. We don't want to lose extra decimal places. We want to represent it properly. And some of you are not going to like this. However, the alternative, what we actually would use, is called propagation of error. And in propagation of error, especially when you're using equations, you have to do standard deviation. And then to figure out how the standard deviation changes when you put it through your equation, you get to do calculus. You're not expected to know calculus. I don't want to do calculus, so we're not going to do propagation of error. That's why we're doing this. This is much simpler than propagation of error. But if you continue on in your science journey, you'll probably learn about propagation of error and all that. We've got 2 sets of rules. We've got rules for multiplication and division. Mathematicians will tell you they're the same thing. So multiplication and division, kind of same idea. And what we care about is which of our inputs has the fewest significant figures. Our answer is going to match that. So for example, 1.052 times 12.504 times 0.53, we would count up 4 sig figs, 5 sig figs, 2 sig figs. Calculator would give us 6.7208. We would say stop at 2 significant figures. So we count over from the left, 6.7, 7's the second number. I usually represent the last significant figure with an underline. This is especially helpful if we were to continue using this number in later calculations. We don't always have to backtrack to the start. So that's our last significant figure. We would then look at the 2 to see how we round. 2 is less than 5, so we round down or truncate. We just drop the 208 at the end. So it turns into 6.7. If we're dividing, this first number has 5 significant figures, our second number has 3 significant figures, that's less, that's fewer. So we would expect 3 significant figures in our answer. Same idea, we count over to our third significant figure. We've got a leading 0. That's just to show us where the decimal place is so we don't lose it. So that's not important. We've got 6, 2, 6. That's our third significant figure. Underline it. We look at the 0. 0 is less than 5, so we truncate or round down. Question?
So let's say you have a problem with like multiple, obviously like multiplication and division operations going on. With every operation, do you do this or do you wait till the end to do this for the final?
So if we've got multiple steps, we want to track our significant figures at each step. And we would only round at the end. One little caveat to this is that anytime that we're putting a number into a data table, it has to be rounded. So this will inevitably cause some confusion. So let's say that I'm using this 0.626. This is a number that I'm reporting. Maybe this is the mass of a bean. We're measuring the mass of beans for some reason. If this is the average mass of a bean, I would put 0.626 in the table. And then if I wanted to estimate, like if I have 50 beans or 51 beans, what would that mass be? I would use the unrounded 0.626094. I would use that number times the 51 beans to get the estimated mass of 51 beans. And then I would round that number and put it into a table. Does that make sense? Question?
So I'm kind of confused on what you mean by track significant figures.
So the little line that I put under it, I recommend doing that anytime you're doing multiplication, division, or addition, subtraction.
Oh, so at each time you're tracking like the least amount of significant figures that have been seen in each of the terms? Is that what you're saying? Like, because you put an underline, I guess, at the third.
Yeah, so the underline at the third significant figure, that's so that I know looking back at this, without counting sig figs inputs, I know that this number has 3 significant figures. The rest of the stuff that's after it is not significant, but if we drop it, then we could end up with a rounding error. In the case of this one, it probably won't result in a rounding error, but sometimes it can change our final number if we round it at each step.
Okay, so each step you want us to do that underline.
It doesn't have to be the underline, but I think that's generally what instructors use to track it. Yeah.
Let's say you multiply that number by something with 2 sig figs, would you just use 2 or would you use the 3?
Yeah, if you multiplied the 3 significant number by something that has 2 sig figs, then it would go to 2 sig figs. Because now we're limited by that 2 significant figures number. Great questions. All right, so that's multiplication and division. We care about fewest significant figures. For addition and subtraction, we care about the least precise number of decimal places, or usually fewest decimal places. A lot of our numbers are typically going to have decimal places. Sometimes they'll be, like our last number is in the ones or the tens or the hundreds column instead. The same idea sort of applies. It's just we wouldn't necessarily call those decimal places. So if we're adding them up or subtracting them, sometimes it's helpful to like draw a line in, and then anything that's after that line we would cut off. So that's one way that you can do it. Typically, we're not going to be writing I usually don't write my numbers like this because I let my calculator do the work for me. So in addition, subtraction, we care about fewest number of decimal places. 2.345 has 3 numbers after the decimal places. We would call that 3 decimal places, DP for decimal places, not Dr. Pepper. For 0.07, how many decimal places? 2 places after the decimal. For 2.9975, we've got 4 places after the decimal. So our fewest, the smallest number is 2. So our answer should also have 2 places after the decimal. So the 1 will be our last significant figure. We look at the 2 to see how we round. 2 is less than 5, so we drop it. So we end up with 5.41. The funky thing about addition subtraction is that if you track the number of significant figures, it can change. So like this 0.07 is only one significant figure. Our final answer, though, has 3 significant figures.
I got one question.
Yeah, question.
So let's say you're doing like addition and subtraction and then multiplication and division and...
Yeah, we're getting to that.
Okay.
Yeah. We'll talk about mixing these two operators or operator sets. So for 5.9, 1 decimal place, just the 9 after the decimal place. For 0.221, the 2, 2, and the 1 are all after the decimal, so it's 3 decimal places. 1 is smaller, so we stop at the 6. That's our last significant figure. We look at the 7 to see how we round. It's 5 or greater, and so we round up to 5.7. Questions about just addition, subtraction? Great. As a reminder for rules for rounding, when we're rounding for the correct number of significant figures, we round down, truncate, just drop them. If the first digit dropped is 4 or less, we'll round up if the first digit is 5 or more. So 24.4 for 2 sig figs. We look at the 4 to see how we round. This would round to 24. If it's 24.5 for 2 sig figs, the 5 now tells us that we round up. That would end up being 25 if we're rounding for 2 significant figures. I think that this rounding method is somewhat contested by some mathematicians. They're not in the room, so we're going to use these rules because they're easier. We're not going to flip a coin every time that we round something, because I think that's one of the strategies. Because 5 is right in the middle, right? So half the time you should go down, half the time you should go up. I think that's the argument. I'm not a mathematician, thank goodness. It's important that magnitude, the general size of the number, doesn't change significantly when we round it. So a common mistake is with big numbers, like the example that we've got down here, $24,938.99. If we round this to 3 significant figures, our third significant figure is the first 9. We would look at the 3 to see how we round. 3 says round down. So 2, 4, 9, and the places after would turn into zeros so that it stays about the same number, right? 24,938.99 versus 24,900. Those are approximately the same number. What you would not want to do, but some people will do, you would not turn this into $249, because that's very different from almost $25,000, right? This would be a sick trick for getting rid of debt. Doesn't work, unfortunately. And so since we've got these trailing zeros, then we get to have some fun, put it in scientific notation. So 2.49 times 10 to the 4 dollars. So make sure that we're not changing our numbers significantly when we're rounding. More rules for rounding. None of those are significant for what I want to talk about. I'll add in though. Let's say that we've got 2.997. We want to round this for 3 significant figures. Our third significant figure is a 9. The number that follows it is a 7. So which way are we rounding? Up. When we round 9 up, what's 1 bigger than 9? 10. So this spot turns into a 10. Where does the 1 and the 10 go? It goes to the 9 in front of it, which turns that into a what? 10. So we put a 0 in that spot. And then where does the 1 from that go? To the 2. So this would round up to 3.00. It is okay for 9s to turn into 10s. Make sure that you retain their spot by adding a 0 for them. This is something that some of us will probably encounter throughout the course of the semester. So I just want to mention it. To avoid rounding errors in multi-step calculations, we round only the final answer or reported answers. We're not going to round off at intermediate answers. We can keep track of significant figures by underlining the last significant digit. Generally, my advice is when we're doing calculations, just go ahead and leave all the numbers on. This is especially easy to do if you've got a calculator where you can just press the up arrow, press enter, and then it pulls the number out for you without you having to retype the whole thing. Like my favorite, the TI-36. I wish I was sponsored by TI. That'd be sick. So we've got a series of steps here. We need to remember a little bit of algebra. Please excuse my dear Aunt Sally or whatever other mnemonic devices you might use for PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. So we do parentheses, exponents, multiplication, division, then addition, subtraction last. We've got stuff in parentheses. So our first step is we're going to do this subtraction since it's in parentheses. The 5.489, since we're doing subtraction, addition and subtraction, we care about decimal places. We've got 3 and 2. We would expect 2 in our intermediate answer. So we get 0.479. Underline the 7 so that we make sure that we know that it's 2 decimal places. So it's 2 decimal places to the underline, including the underlined number. And then we switch to multiplication. Since we are switching to multiplication with these 3 numbers, we've got 6.78, 5.903, 0.479. Our first number, 3 significant figures. Our second number, 4 significant figures. Our last number, our 0.479, how many significant figures? 2 significant figures. We stop at the underline. So that's 2 significant figures, and so we would carry through 2 significant figures to our answer. So the 9 would be our last significant figure. We look at the next digit and only the next digit to see how we round. 1 smaller than 5, so we round down or truncate, turns into 19. Question?
So I'm just kind of confused. I guess so. Like, let's say like the second thing, like under the first expression, like was all in parentheses, and then it was like subtracted something with like a different amount of like significant figures and decimal places that we got in the final answer. Like, would we take like, let's say it was like minus.
So if we've got extra steps, right? If we're not just doing 2 steps, whatever step we're working on at the time, we consider the decimal places or the significant figures. and we can swap back and forth kind of as many times as called for in our example. A lot of the time, we're not going to be doing two operations at once. Usually we're doing addition and subtraction, or we're doing multiplication division. Usually we can break those down into individual steps in our labs. All right, I'm going to give you some time to work on these. So perform each of these calculations to the correct number of significant figures. Please feel free to discuss with your neighbor, ask them questions, review things, etc. I'll give us a couple minutes. So for each of these calculations, we want to do them correctly. We need to think about our rules for addition, subtraction, multiplication, division, and making sure that we're doing our order of operations correctly. For our first calculation, we've got all multiplication division. So we just care about what? Fewest number of significant figures. So we care about the fewest number of significant figures. So we need to count up how many significant figures do each of our numbers have. Our first one, we've got some interior zeros. These are all going to be significant. So we've got 6. Sig figs 9.441. 4 significant figures, 0.0301. 3 significant figures. And our last number with the weird 3 has 4 significant figures. I don't know why this last 3 is like in a different font and maybe not bolded. Who knows? I don't. So 3 significant figures is our fewest, our smallest number. So let's see what the calculator tells us. 3.10007 441 times 0.0301 divided by 2.313. Calculator says 0.380873153. We would count over for 3 significant figures to this 0. It's going to be our third significant figure. Look at the 8 to see how we round. This will round up to 0.381 to have 3 significant figures. For B, we're doing addition, subtraction. What do we care about? Decimal places. So we've got 3 decimal places, 1 decimal place, 2 decimal places. So we expect how many in our final answer? 1 decimal place. So 0.881 plus 132.1 minus 12.02. Calculator says 120.961. For 1 decimal place, that's going to be our 9. Look at the 6 to see how we round. This would turn into 121.0, because our 9 rounds up to a 10. C and D, we've got mixed operators. For C, we're going to start with our parentheses. So we're doing addition, subtraction first. We already covered, we're talking about decimal places. So we've got 2 decimal places, 3 decimal places. We're going to get some intermediate number here. It should have 2 decimal places that are significant. We're going to include everything else, but we know that only those 2 decimal places are significant. So 44.11 plus 1.223. Calculator says 45.333. Our second 3 is our last significant figure. It's our second decimal place. We don't round because we're going to use this number for some other things. So now we're going to switch modes. We've got multiplication and division. So now we care about number of significant figures. And this is 4 significant figures. Our other numbers are 5 and 4 significant figures. So we do 2.511 times 21.2 divided by our intermediate answer, including the last 3. And the calculator says 1.1742 and some change. And our fewest number of significant figures was 4. So we count over to, conveniently, a 4. Our fourth significant figure, round down to 1.174. For our last one, we've got multiplication in our parentheses, and so we're going to do multiplication first. We care about significant figures. We've got 4 and 1. So we expect one significant figure in our intermediate answer. 12.01 times 0.3, 3.603. The first 3 is our only significant figure. And then we switch gears. We're doing addition next. So we're adding 3.603 to 4.811. This is what I would call 0 decimal places, or our last significant place is the ones place. So we would expect to stop with our final answer at the ones place. The ones place will be our last significant place. So add to that 4.811. Calculator says 8.414 for 0 decimal places, or the ones place being our last place. The 8 is significant. We look at the 4 to see how we round. We're going to truncate or drop or round down to 8. Questions about any of those 4 examples? Yes?
So it makes sense to me not like now, but I guess that's what I was gonna ask you about. Is like we don't like use the last steps rules to round. Like we use like whatever's like least, like you know what I'm saying? Because like the last step of addition, and like but we don't look at the 2 numbers that we're adding in the end, like to see like how it should round.
So it's kind of a process, right? So we looked at the multiplication here first to figure out how many our intermediate number has. And then we switch rules to do this last step. We wouldn't go to 1 sig fig just based off of this 0.3 at the end. We wouldn't do it because of that. It works out that way in this case. But there's other instances where we might end up with, like if this was, let's make it 8.811. Then instead of the number that we got, we would get 12.414. And we would also be rounding for the ones place, being our last significant figure. And so that would instead be 12. So we'd have 2 significant figures. So that's why we have to go in a process of steps. Question?
For the last one, why would you use the multiplication division rule over the addition subtraction?
So we use this one first. We use the multiplication rule first to figure out how many sig figs come out of the stuff that's in parentheses. So we end up with 1.
So it depends which process is used first. So like if you were to switch the multiplication to addition for that problem, so 12.01 plus 0.3, and multiplied by 4.811, would you use the addition subtraction property first because it's under the parentheses?
Yeah, so whatever's in parentheses, that's why we do the PEMDAS.
Okay.
So we do it in that order to figure out what we do first. Any other last questions? Great, then we'll wrap up there for today.